let's make a start. So continuing, I guess, the trend of random temporal graphs, we've got Gabor Lugosi now talking about paths and cliques in random temporal graphs. So Gabor, the floor is yours.
Thank you, Eleni. Thanks so much for inviting me. I would have loved to be there in person, but it coincided with another trip, so sorry about the online talk. Okay, let me try to make this full screen. Then. Is this okay now?
Yes, that's great. Thank you.
Okay, so I'm gonna show you a few things that we proved about random temporal graphs. I'm going to summarize the results of a few papers without going too much into technical details. So this is joint work with Kalen. He's a PhD student at McGill University. Nick Brutin, he's in Paris. Luc de Broy is at McGill, and Nina is a professor in Zagreb. Okay, so I've seen that in every talk, a temporal graph is a different thing. So let me give you the definition of what we mean by a temporal graph. So a temporal graph is just a graph where the edges are ordered. So the edges have these timestamps. There's the first edge, the second edge, and so on and so on. Okay, and we say that an edge precedes another edge if the timestamp is smaller than that. Okay, so if you can think about these as arrival times of the edges. So these temporal graphs, as all of you know, model time-dependent propagation processes. You can think about propagating, let's say, in epidemiology, the spread of a disease. When vertices of this graph may represent people, and the timestamp of an edge represents the time when they meet. Okay, so what this means is that if somebody is infected before an edge appears, then the infection will spread over this edge. So what this means also is that the infections can spread along monotone increasing paths. So in the study of these increasing paths is fundamental in these graphs. So this is just a simple cartoon of what's happening. So this is a graph with 9 edges. So this is edge number 1. This is edge number 2, edge number 4, and so on. And let's say this vertex is patient 0. This is the vertex who was infected at let's say time 0. What this means is that the first time this patient can this vertex can infect somebody is number 3, right? And then the disease can spread along these monotone paths. Okay, so 3, 5, 7 is a monotone path. 3, 5, 8 is a monotone path. 9, this is a monotone path. 6, 7 is a monotone path, all emanating from this vertex. So I think these are the only monotone paths starting at this vertex in this example. Please interrupt me if there's any question. Okay, so in this talk, we consider the case when the underlying graph is an Erdős-Rényi random graph, which simply means that we have n vertices, and each pair of vertices are connected independently of all the other connections with probability p. And the nice thing about this model is that we can also generate so this is an Erdős-Rényi random graph, and the edge labels are going to be just a random permutation of the edges. Okay, so the nice thing about this model is that we can generate them in several ways. Another way of generating this temporal random simple temporal graphs is that we start with a complete graph on n vertices, and we label each edge with a uniform random variable. So for each edge, there's an IID uniform random variable, and we keep an edge only if it's at most if the label value is at most p. So this means that each edge is there with probability p, right? This is p, and these uij's are just the timestamp. They give us the ordering of the edges. Okay. So I will denote this random temporal graph by G of U. U meaning the collection of these timestamps. All right. So this model was introduced formally in these two papers. These are two really nice papers where the basic connectivity properties are established. In particular, one of some of the main results are summarized here, and these results say that the critical value of P when the connections appear are of the order of log n over n. And in particular, if okay, there's a mistake here. This should be the other way around. So if you take two typical vertices, then if P is smaller than 1 minus epsilon times log n over n, then there will be no monotone path between those two. But if P is greater than 1 plus epsilon times log n over n, then two typical vertices will have a monotone increasing path actually in both directions. Okay. You can also these papers also asked what happens when can we say that a vertex will a typical vertex will infect all other vertices, and for this the threshold is around 2 log n over n, meaning that if P is less than 2 minus epsilon times log n over n, then a typical vertex will not infect all other vertices, meaning that it is not true that there is a monotone path starting from, let's say, vertex 1 and reaching all other vertices. But if P is greater than 2 plus epsilon times log n over n, then it will reach all of this. This is true for every positive fixed epsilon. And the whole graph is temporally connected, meaning that from every vertex there's a monotone path to every other vertex if P is greater than 3 times log n over n. But if P is less than 3 times log n over n, this doesn't happen. So these were the basic results that show also that somehow the critical interesting values of P are of the order of log n over n. Okay? So even though these were the papers that actually introduced this model formally, the same model had been studied before. Let me just jump one vertex here. Okay, sorry, I'm running ahead. So what I'm interested in the first part of this talk is how long these paths are. Okay, so what is the if between vertex I and j there may be many monotone paths. So little l of I and j is the shortest of these, and capital L of I and j is the longest monotone path. Okay, so we can study the length of the shortest and the longest monotone path between two typical vertices. So typical vertices are, let's say, vertex 1 and vertex 2. Right? So these are just any two fixed vertices. We can ask what are the typical lengths between what are the typical values of the longest and the shortest path between these. We can also ask what is the longest path starting from a typical vertex and reaching anywhere. Okay. We can ask what is the longest, shortest path starting from a vertex and then going to any other vertex. And we can also talk about the longest path in the entire graph and the longest, shortest path. So this is just the so-called temporal diameter of the graph. Okay. What is the longest, shortest path between any two vertices? Okay. So as I said, this model has actually already been studied before these papers that I mentioned. Angel, Ferber, Sudakov, and Tassian, they arrived to this problem from a completely different angle, and they studied the longest monotone path in a simple random temporal graph. And what they showed is that if P is little of n, sorry, this should be a little of 1, so if P goes to 0, but it goes to 0 slower than log n over n. So if P is much larger than log n over n, then the longest path is typically of length E times n times P. Okay? And this excludes the somehow interesting regime where P is of the order of C times log n over n, because we saw that in terms of connectivity, that's when everything happens. In fact, we can combine these results and then show very simply that not only the longest path is of this order e times n times p, but also the longest path between any two vertices. And a very simple way of seeing this, very simple way of seeing it is that we can simply construct. So let's say we want to show that in this regime when p is much larger than log n over n, there is a long path between vertex 1 and vertex 2. And what we can do, and this is a technique that we use a lot in these proofs, is that we can partition the interval. So remember, the time labels are these uniform random variables that take values between 0 and p. We can chop this interval into in this case 3 pieces, and the middle piece is going to be the longest one. This piece is about as long as the whole thing, and we know that the longest, there exists a long path between two vertices of length about e times n times p, only using time labels from that interval. But then from vertex 1 to the starting point of this long path, we can find a long path because of this result here. We can find a long path that leads from vertex 1, a long monotone path that leads from vertex 1 to vertex to the beginning of this longest path. So this way we can construct a path along of about this length between any two vertices, not just the longest path. Okay. So in order to describe the main results about these longest and shortest paths, we need to define some constants. So all these constants have to do with this function x log x, okay, or x log x, and that has this parameter c, where c is remember c is the value of p is c times log n over n. Okay, that's going to be our c. So x log x is a convex function that starts at 0, then it dips down to negative values. At some point, it crosses 0 again, and then it increases. So what that means is that this equation has just one solution. But this equation, when x log x goes down to negative values, and it may or may not hit -1. So this equation may have 0, 1, or 2 solutions. And beta of c is the largest solution, and the gamma of c is the smallest of these two solutions. Okay, so this is what I just told you about. If c equals 1, then the second equation has only one solution. And if c is smaller than 1, there's no solution. And if c is greater than 1, then there are two solutions. Okay? All right. So here, these are the main results about longest monotone paths. So suppose that p, the connection probability between any two vertices, is c times log n over n. Now we know from these previous results that if c is smaller than 1, then there is no increasing path between vertex 1 and vertex 2 with high probability. But if c is larger than 1, then there exists one, and the longest one is of the order of beta of c times log n. So remember, beta of c is the largest solution of this equation. So that is the typical length of the longest increasing path between vertex 1 and vertex 2. Now, between vertex 1, the longest path starting from vertex 1 and reaching anywhere, that is larger, and that is of the order that is linear in c, and that's like e times c times log n, which remember is the same as that b times e times n, which we saw in this result of Angel, Ferber, Sudakov, and Tassian. Okay, so this is the length of the longest path starting at vertex 1 and reaching any other vertex. And the longest path overall in the entire graph is alpha c times log n. For example, if c equals 1, then the value of this constant is this 3 times 5, 9. All right. So, what about the shortest paths? Well, they involve this constant gamma c, which is the smallest solution of that equation, and we have these three expressions. All right. So how does one prove such a thing? Well, one side of the inequality is easy. The upper bounds can easily be found by simply considering first moments. Okay. So let's say if we want to understand the longest path longest monotone path in the entire graph, then we can just consider the number of increasing paths of length k. Okay? So how many are what's the expected value of these? Well, we have to choose the k+1 vertices that form this increasing path. Oops. Sorry. Then we have to order them, right? There are k+1 factorial ways of ordering them. So, and then once we have an ordered path, what's the probability that it's a monotone path? Well, every edge, there are k edges in this path. They all have to be open. So the probability of that is p to the k. And the labels have to be monotone, and the probability of that is 1 over k factorial. So the expectation is about n times NEP divided by k to the power of k, and which means that there is with high probability, if this goes to 0, then with high probability there's no increasing path of this length, and this is where the upper bounds come from. And you can see when you solve this equation to k, this is where this alpha, beta, and gamma, all these constants come. Okay. Similarly, we can compute the expected number of monotone paths starting from vertex 1. Okay. So here we have only n-1 possible vertices to choose from, but we only have to choose k vertices, and that's why this factor n disappears here. And when we consider paths going monotone paths between two fixed vertices, then we only have to choose the k-1 vertices in between those. So this is where the upper bounds come from. The challenge is the lower bounds. I don't have too much time to go in these. There are different techniques to prove all the different lower bounds. One of them that maybe I should mention. No, maybe I'm not going to mention anything. Sorry about this. There are no proofs and stuff. Okay. These are still proofs. Okay. All right. So we already studied what we call temporal cliques. So what's a temporal clique? A temporal clique is just a set of vertices such that everybody infects everybody. Okay? So a set of vertices form a temporal clique if there's a monotone increasing path between any two vertices, okay? And vice versa, so in both directions. Okay? So what a key concept in the connectivity of these random temporal graphs is what is the size of the largest temporal clique. And this was studied in this paper of Becker and co-authors who showed that there's a really interesting phase transition going on around p equals 1 times log n over n. Okay? So in particular, they showed that if they call this a giant component. Okay? So what they showed is that if p is larger than 1 times log n over n, then basically almost everybody is in a temporal clique. So there is a subset of vertices that contains all but very few vertices, such that they all infect each other. But if p is smaller than log n over n, then the largest temporal clique is of the size little of n. Okay? So there's a sharp, at least at this scale of log n over n, there's a very sharp transition going from essentially nothing to essentially everything. Okay? And we were interested in what this essentially nothing actually meets. How can we quantify this? Okay? And what we could prove is actually quite surprising. What it says is that if p is less than log n over n, then the size of the largest temporal clique is not only little of n, but actually it's of size constant. It's of constant size. So the largest temporal clique has at most this many vertices where c is this constant. Okay? So clearly, if c is close to 1, then this will become larger. But it's very interesting that the temporal clique number, the size of the largest temporal clique, jumps from constant to n minus a little of n in this small window. Okay? So this is only an upper bound. We believe that this upper bound is actually correct. We know that it is correct when c is at most 1/2, because if c is at most 1/2, then this upper bound is 3. So it says that the probability of connection is at most 1/2 log n over n. Then there are temporal triangles, but that's it. There are no 4 vertices that are temporally connected. And but we know that there are temporal triangles because any triangle in G and P is a temporal triangle. And that in this regime there are lots of triangles. So we know at least that when c is less than 1/2, then this is correct. We conjecture that this is also true. It's a nice open question to think about. Okay, so how do we prove this? Again, I don't have time to go into the details, but the proof of this uses the fact that these random graphs, G and P's, are, when P is small, they are locally tree-like. Okay, so when we look at the neighborhood of a vertex, then for a while, when the neighborhood is still small, then this is a tree. Okay? So this led us to actually define a model of random trees that we called uniform temporal trees, and this is such a beautiful model that even when we proved what we wanted to prove about these cliques, we started to study these uniform temporal trees. So let me just say a few words about what we discovered here. So what's a uniform temporal tree? We start with a rooted, complete, infinite n-ary tree. So what this means is that there's a root. The root has n children, and now every child has n children, and so on. So if n is 2, then this is just a complete infinite binary tree, n is 3, the ternary tree, and so on. Okay, so we start with such a tree, and we assign an independent uniform random variable to every edge. Okay? And now we will only keep those paths starting from the root over which the timestamps, the labels, are monotonically increasing. Okay? So this is a uniform temporal tree, and then there's the p-percolated version of this, where we only keep those edges where the labels are at most p. Okay? So these are, of course, relevant for our G and P. Okay, so that's the definition. This is what such a tree looks like. Okay, so this is the root. This is when n equals 10. So there are 10 children here, and now on every edge there's a uniform random variable, and then the children. So whenever now there's an edge here whose timestamp is smaller than the timestamp here, then that edge is cut down, that dies out. Okay? So the only surviving paths are those over which the edge labels are monotonically increasing. This is what it looks like. Okay, so the first thing that you can ask is what's the size of how many vertices are there in this tree? It's very easy to see that this tree is almost surely finite. So it will die out because so that's an easy exercise. The expected size is also very easy to compute, because if we look at any vertex in the complete n-ary tree at depth k, what is the probability that vertex survives? Well, the path has to be open, and that the probability of that is p to the k. All the edges, edge labels have to be below p, and we need monotonicity. Okay, so the expected value is just this this infinite sum, which is exactly e to the n. Okay? We can also prove that the size is actually not concentrated around this level, but the size divided by e to the np converges to an exponential random variable as n goes to infinity. Okay. We also know what are the subtree sizes around the root. So if vi is the child of the root with the ith largest timestamp, then the joint for any fixed m, the joint distribution, the joint relative size of these subtrees compared to the total size of the tree converges to an exponential times a uniform. This is going to be the size of the first subtree. The other is an independent exponential times a uniform times another uniform. This uniform and this uniform are the same, and so on. Okay, so these are IID exponentials and IID uniforms. So we have a nice description of how the weight is distributed among the children of the root. We can also look at the height of this percolated uniformly random tree. The height is just the longest path. Okay? And the longest path is about e times the log of the size of the tree. Remember, the size of the tree is e to the np. So so what this means is that the longest path is logarithmic, and it's the length is e times the log of the number of vertices. If we take a uniformly chosen vertex, then its depth, its distance from the root is about 1 times the log of the size of the tree. And we also have results about the degree distribution. So if the number of vertices of out degree k for any fixed k is the proportion of this is about 2 to the minus k. Okay? So in particular, if k is 0, that counts the number of leaves. So what this says is that around about half of the vertices are leaves. It's very interesting that all these results, the height, depth, and degree distribution, they are exactly the same as what you get in a so-called uniform random recursive tree of this size. Okay? A uniform random recursive tree is just a tree where we start with a vertex, the second vertex attaches to it, and whenever a new vertex comes, it attaches to a previous vertex uniformly at random. Those are uniform random recursive trees. They have been studied a lot. All of these notions are well understood, and we have exactly the same kind of behavior here. These are different trees, though. They don't have the mass distribution at the root is different, but it's kind of nice that we have this kind of analogy. So let me just finish the talk by a few open questions that we don't know. What is the length of the longest path when p is a constant? Remember, we have to assume that p goes to 0 in order to get our results. So when p is constant, then things become complicated. What happens between that 1 minus epsilon log n over n and 1 plus epsilon log n over n in a smaller case? What is the size of the critical window? The optimality of the clique number I mentioned already. We can also think about different random graph models apart from G and P. And these are the papers that I talked about. So the increasing paths are in this paper with Nina and Nick. And with Luc and Kalen, we have the paper on the temporal cliques and the uniform temporal trees. And one paper I did not talk about is about the temporal connectivity, but in a different random graph model in random geometric graphs, where it's kind of interesting new phenomena. Okay, I think my time is up, so I'm going to stop here.
Thank you, Gabor.